Hi, everybody.
Hello.
Hello, everyone.
So I think it's time to start, right? So I'm very happy to welcome you on behalf of the organizing committee to the second edition of the workshop on performance and energy efficiency in concurrent systems. We're very glad that we have been able to organize this second edition. And for this, we want to thank all the authors who have put much effort into preparing some very interesting papers that will be part of the upcoming technical session. I want to say that it is not obvious to be able to organize a workshop because the number of conferences to which today is possible to send an article is always larger. We believe that this result is a proof of the importance of the trade-off between performance and energy efficiency in systems of all kinds. And we also want to take an opportunity to thank the workshop chairs for their assistance and support during the preparation of the workshop. So now, it's a pleasure to open the second edition of Pecs with a keynote speech by Professor Pierangelo Di Sanzo of the University of L'Aquila. In his talk, he will talk about heuristic-driven versus model-driven performance optimization of multi-threaded applications under a power cap. So, hi Pierangelo, the floor, or better, the virtual floor is yours.
Thank you. Can you hear me?
Yes.
Okay. Thank you, Alessandro, for your introduction. Let me start my slide. I want to share my screen. Okay. Okay. Can you see my screen, please? Can you give me a feedback?
Yes, please go ahead.
Okay. Thank you. Okay. So let's start. Let's start my keynote speech with an overview of related to what recent studies say about the climate and the transformative impact of ICT. To do so, I reported, I want to read just a few sentences from a very recent paper, this one, The Real Climate and Transformative Impact of ICT, a critique of estimates, trends, and regulations. This is a very recent paper that summarizes the current. I think that provides a good, a very recent view of what we are going in the context of climate and transformative impact of ICT. Let me read this set of sentences. The first one, global emissions from ICT are as high as 2.1 to 3.9% of the global greenhouse gas. The second one, all study analysts agree that ICT emission will not reduce without measured concerted political and industrial efforts. Additionally, another sentence from this paper says there is a pressing need to devise a strategy for constraining consumption of ICT so that efficiency improvement lead to actual emission reduction and enable productivity to be maintained in a carbon-constrained world. As a conclusion, I reported this sentence: the climate emergency requires a global constraint such as a carbon cap on extraction, a price on carbon emissions, or a constraint on consumption to rule out rebounds in emissions. With this in place, the ICT-enabled carbon reduction could be realized, and the ICT industry could become a vital sector from the transition to a net zero world. In summary, if you take a look at these sentences, I've evidenced some keywords, some basic keywords, like constraining, as you can see. Can you see my mouse pointer, please?
Yes.
Okay, thank you. So constraining, carbon constrained world, carbon cap, or a constraint on consumption. Okay, this constraining is a very important are very important keywords here because they give the what we really need in the context of ICT. So essentially, we need to be able to put a power cap on the ICT, on the global ICT. A power cap, obviously, that can change over time, depending on what we really need on the future evolution of the global condition about energy footprint, about the carbon extraction, about the impact on climate change of by the ICT. So, if we want to be able to limit the global ICT power consumption, obviously we have to be able to limit the power consumption of data centers. We have to be able to put a power cap on data centers. In terms to do so, we need to be able to limit the power consumption of a single server. Obviously, this power cap that we can set is dynamic. It depends on the power consumption of the other thread we need within a data center. However, the goal is to be able to put a power cap, a dynamic power cap. In short, if we want to be able to limit the power consumption of a server, we should be able to limit the power consumption of a single application. We should be able to assign a power budget, a limited power budget to the different application running on a single server. Basically, application power capping means that if we have an application, this is just a simple general case. If we have an application, this is the curve of the power consumption along the application. We should be able to decide the power constraint so that we can limit the power usage of the application along the lifetime of the application. And obviously, this should be an arbitrary constraint, an arbitrary power cap that we can change depending on the external conditions. Today, we know that multi-core computer architectures represent the mainstream architectures. So, this kind of architecture, the computing power of this kind of architecture can be effectively exploited by multi-threaded application. If we use multi-threaded application, we can use more than one core within a single server. The problem is that obviously, if we increase the number of threads within an application, we increase the number of used core. This is just an example. If we have a 6-core machine, if we increase the number of threads, we use more cores, and this means that we use more power, because obviously the power is equal to the sum of the power consumption of the different cores. So increasing the number of threads has an impact on the power consumption, but we will know that changing the number of threads, if we change the number of concurrent threads within an application, this can have a non-minimal impact on the performance. At the same time, modern multi-core processors provide various hardware facilities to control the power usage of processor. In particular, there are operating systems offer power management tools like the Linux CPU frequency governors, which easily allow to control the dynamic voltage and frequency scaling. That is the frequency and the voltage of the different processor cores via the abstraction of P states. Essentially, P states represent a core frequency setting. P state 0 represents the case where we have the highest frequency, the highest core frequency, and obviously we have the highest power consumption. While moving from P state 0, we can change the state. We can change to P state 1, for example. In this case, we reduce the core frequency and we reduce the power consumption. So we can reduce. We can increasingly reduce the core frequency and the power consumption. And similarly to the case of the number of threads, also changing the core frequency has an impact on performance. In particular, the number of instructions per second with P state 0, with the P state with the highest frequency, is greater than the number of instructions per second that we can execute with P state P1, which is greater than the number of instructions that we can execute with the state 2, and so on. So while changing the core frequency, we can change the power usage, but also in this case, we have an impact, a noticeable impact on performance. So in short, both number of concurrent threads, that is the number of cores that we can use that an application uses, and the frequency, the core frequency that we set, has an impact on the application power usage and the application of the performance. If we want to be able to set a power cap, if we want to set a power cap on the consumption of the application, obviously we should be able to maximize the performance under this power cap by setting the proper number of concurrent threads and the proper frequency, so that the power cap is not violated by the application, and the performance that we can achieve is the maximum that we can is maximum between the different configuration. Obviously, if we want to be able to maximize the performance under a power cap, there is a key factors to be accounted for, which is the scalability profile of the application. If we increase the number of used core by increasing the number of concurrent threads, typically we can see in most of times something like this: the throughput increases. However, this is not always the case. There are other situations where we can see that the throughput increases, and after there is a plateau, like in this case, profile 2. In other cases, the throughput while we increase the number of concurrent threads, the throughput initially increases, there is a peak value, and after it starts decreasing. And in some extreme situation, in the worst case, let's say, while increasing the number of concurrent threads, the number of used core, the throughput immediately decreases. These are real situations that many times we can find in a lot of applications. In short, profile 1 represents the case of high scalable application. This represents the case where with the limited scalability. This represents the case where there is a peak and then the throughput decreases. And here, this is towards the case where the workload of the application does not scale at all. This means that we use just 2 cores for running the application for various reasons, in particular due to the contention of different resources, the throughput immediately decreases. If we try to change p-state, that is if we try to execute the application with different p-state, that is with different core frequency, we can observe something like this. The different colors, the different curves here are represented by different colors. Each color represents a different p-state. So you can see here p-state 0, p-state 1, p-state 2, and so on. By running the application while changing p-state, we typically can observe something like this. The throughput, if the profile of the application, if the profile with the fixed p-state of the application always increases, also if we change p-state, the throughput always increases. As you can see, the curves are very similar each other. Similarly, with profile 2, with this case, similarly with profile 3, as you can see here, the peak does not change. With the number of threads where we have the peak throughput is always the same. And also in this case, the throughput, maximum throughput is always with one core. So in short, this means that the shapes of the curve do not change. They are not affected, the shape of the curve are not affected by the p-state variation. If we take a look at the power usage in the same condition, this is a very is a case. This is corresponds to the first case: profile 1, profile 2, profile 3, and profile 4. We can observe that the curves are very similar. All curves are very similar. So while increasing the number of used core, the throughput or the power usage always increases independently of the throughput profile. In summary, we can see something like this. The power usage, which is represented by these pictures here below, is very similar in each case. But the throughput can notably change in particular in profile 3 and profile 4. This makes not so simple to identify the best configuration that provides the highest performance without violating the given power cap. And the main aspect is that we should be taking into account the scalability profile of the application. Here, in this case, it's very simple to find the best configuration, the configuration that provides the highest throughput. We increase in the number of used core until we do not violate the power cap. However, in this case, it's not the same case, because if we increase the number of cores, at the same time the throughput starts decreasing. Even more here, increasing the number of concurrent of used core, the throughput immediately starts decreasing. So, for example, in this situation, we are using a lot of energy, but we are achieving poor performance. So the scalability profile of the application must be taken into account. If we want to try to resolve this problem, the first step is to be able to identify within the search space, within the solution space. In this case, the solution space is given by the number of used core and by the frequency setting, the P state of the core. We are considering the problem of maximizing the performance under a power cap. And we have two control knobs, the number of used core of the application and the P state of the core used by the application. So let's define a configuration as a couple Pn, where P is number of P is the P state number, and N is number of used core. So if we have a power cap, we can define an acceptable configuration as a configuration that does not violate the power cap. And so the set SAC is composed of the whole configurations that does not violate do not violate the power cap. All the possible couple of number of P and N for which the power cap is not violated by the application. The other one are an acceptable application, because this means that the application is violating the power cap. So since while increasing the number of used core and while decreasing P state, in both cases the power usage increases, we can identify a frontier line that separates the set of acceptable configuration and the set of unacceptable configuration. So the problem is exactly this one. We want to find within the set of acceptable configuration the best configuration, that is the configuration that provides the highest performance. To this aim, let me introduce some notations. As I said, we can identify a configuration as a couple Pn, the P state number, and the number of used core. Let's define power Pn, the power usage, the measure of the power usage with this configuration, with configuration Pn. The throughput Pn is the application throughput the application performance that we can measure with this configuration Pn. C is the power cap value. S is the set of all configuration, and as I said, SAC is the set of acceptable configuration. By using this notation, our goal can be defined in this way. We want to find the configuration Pn optimal in the set of acceptable configuration, such that the throughput with this configuration is the best one, is higher or equal to the throughput with any other configuration, the throughput with Pn. So Pn optimal is the optimal configuration. We want to find this configuration. To to this goal, to reach this goal, I want to discuss two alternative approaches, typical approaches that we can use in various set of problems related to optimization of some kind of application, of non-functional aspect, of non-functional feature of an application. In particular, in this case, we are considering performance and energy efficiency. These two alternative approaches are the so-called heuristic-based approach or model-based approach. The first one, the heuristic-based approach, in this case, I want to focus on an exploration-based strategy that tries to search within the bidimensional space, bidimensional configuration space, the optimal configuration. So this works as an exploration, using an exploration approach. The other one, the model-based approach relies on the use of analytical models, on the use of a performance model and of a power usage model that predict the performance of the application and the power usage of the application with the different configurations, so that we can use the prediction by the models in order to identify the best configuration to our aim. These are two very different approaches with different basic assumptions. In effect, the exploration-based strategy, a basic exploration strategy could try to find the best configuration within the whole bidimensional space by exploring the whole bidimensional space. However, the whole space often can be very, very large, when in particular where we have a machine with a high number of cores, or additionally when we have a processor with a high number of p-states. So exploring the whole bidimensional space is typical, in general, is costly. To this aim, if by the observation that we made before about the profile, the scalability profile of the application and the power usage profile of the different applications, we can make some assumption for reducing the exploration space. The first one is the so-called unimodality. That is, we can assume that throughput curves are unimodal. As you can see, the unimodal here is all curves here, all curves that you can see here matches with the unimodal assumption. In fact, here the curves always increases. Here increases and there is a plateau. Here increases, there is a single peak and then decreases. And here also there is a peak here and then decreases. So the unimodal assumption here can be considered a good approximation of this of the behavior of this of all these profiles. In particular, if we change the p-state, as you can see, the unimodality assumption always matches. As for the second assumption, we assume that power usage always increases as a function of concurrent threads, that is as a function of the used core. And this is a very trivial assumption, because as you can see, this is this holds in all cases. So if we use this assumption, unimodality in this one, it is possible to define an exploration-based strategy which is able to identify the optimal configuration only exploring a small subset of the configuration space. Let's focus on this aspect. This exploration strategy, in particular, based on the previous assumption, can define the optimal configuration in linear time. Why? Essentially because assume that we are exploring, we are moving along the bidimensional space. If I give, and we at runtime we select a given configuration, we measure the throughput of this configuration, the application throughput, and then we try to reduce the number of used core. If the throughput with n core is less or equal to the number of to the throughput with n minus 1 used core, then this means that all configuration p prime n prime, where n prime is greater or equal to n, for whichever p state, can be removed from the search space. Essentially, this is because we are in the descending part of the throughput curve, and all throughput curves preserve the shape while changing p state. If we detect this situation, we need that we are essentially are exploring, for example, along this direction. If we are moving along this direction, based on the unimodality assumption, there is no there may be another peak cannot exist here. So if there is a descending part of the curve, this means that the throughput peak is before. So essentially, if we detect that throughput curve is decreasing, we can avoid to explore all this space for whichever p state. Similarly, if we measure the power consumption with the given configuration, the power consumption is below the power cap. This means that all the configuration with the p state number greater than p can be removed from the search space, because if we increase p state, we reduce the application throughput because we are reducing the frequency. So we are reducing the frequency. So as a consequence, we are reducing the application performance. If we use this p state, and this configuration pn, and this configuration does not violate the power cap, this means that we can avoid to explore the power and the throughput with the number of p state greater than p. So we can remove another set of configuration. Finally, if we find the configuration with the power such that the power cap with this, the power usage with this configuration is violating the power cap, this means that we can remove from the search space all the configuration p prime, n prime, for which n prime is greater than n and p is lower than p. Because if we if this configuration violates the power cap, and we increase the number of used core, the power usage increases, so we can avoid to explore this configuration. And similarly, if we decrease p state, we are increasing the power consumption, so it's not useful to explore this configuration. By using this these results, we can define a simple basic exploration strategy that works in 3 phases. I want to just provide you an idea or about how we can how this exploration-based strategy can work. We can start from a random configuration. Assume that this is the starting configuration, a random selected configuration. PS and NS, P start and N start. We can start moving while keeping fixed P state and increasing the number of used core. We move toward this direction and we measure the power consumption and the throughput. As soon as the power consumption overcome a given the power cap here, as you can see here, we are overcoming the frontier. This means that we can avoid to explore all this configuration. We come back here and we terminate the exploration. The second phase starts from here and try to follow the line, the frontier line. And essentially, it explores all the adjacent configuration along the frontier line. And similarly, the third phase behaves in a similar way until the power cap is violated. By exploring this subset of configurations, this one, and this one, we can demonstrate that we can find the optimal configuration without exploring the other subset of configuration. we can provide them, we can achieve a mathematical proof of this. However, I don't want to focus on this specific aspect. If you are interested in this, I can share with you the paper where you can find the specific mathematical proof of this aspect. The key aspect is that these two assumptions are fundamental to this aim, to define this exploration-based strategy. The time complexity of the exploration-based strategy can be easily estimated. In the phase one, we can explore at most n-max configuration, where n-max is the maximum number of cores of the machine. In the phase two, we can explore at most Pmax plus n-max configuration. As, in short, we move in this direction here. So in the worst case, we explore from here to here. And similarly, in the third case, we can explore at the most Pmax plus n-max configuration. So finally, the complexity of the exploration-based strategy, as you can see, is linear. In particular, is a big O of Pmax plus n-max. Let's move to the model-based strategy. As I said, the model-based strategy uses two analytical models to estimate the throughput and the power usage. Obviously, in order to build this model, in order to instantiate this mathematical model, we need to sample in a subset of configuration, a subset of configuration space, in order to create an instance of the model that fits with our specific problem. The model-based strategy works in three phases. However, these three phases are very different compared to the previous one. In the phase one, the throughput and the power usage are estimated for a predetermined set of configuration. Then the model are instantiated by solving the set of equations. And in the third phase, the throughput and the power usage for those configuration are estimated through the two analytical models. And then we can select the best configuration, that is the configuration with the highest throughut that does not violate the power cap. Using models, mathematical models for the throughput and for estimating the power cap, we can avoid to make the assumption one and the assumption two, as in the case of the exploration strategy. So essentially, the model-based strategy does not require assumption one and assumption two. Assumption two is generally able to identify the best configuration without relying on this assumption. We can, let me focus just a few on the model construction, but I don't want to go into details because there are many mathematical details. I want to just provide them a general idea of how we can build a throughput model for this kind of application. If we define T, the execution time in general of a computational task, the execution time can be calculated as the sum of two components. C is the execution time of the CPU bound portion of the task operation. C essentially is the portion of the operation subject to the variation of the frequency of the core, because this represents the instruction executed the CPU bound set of operation. And M is the set of is the execution time of all the operations that are not affected by the frequency variation of the core. For example, such as memory operation. When we access the memory, the speed of the operation is independent of the specific frequency of the given core. So we can estimate the execution time for a given P state, for a given frequency, using this formula where if we measure the frequency and the execution time for a frequency fj, for example, the ratio between fj and f key, where key is the f key, the frequency, the P state where for which we want to estimate the execution time, can be estimated using this fraction, the ratio between the initial frequency and the final frequency. Obviously, this, as I said, affect only this part, only the C component of the execution time. by using this approach, we can estimate the execution time for whichever p-state key while running with the given number of core equal to n. However, to do so, we need to sample, we need to estimate C and M for the different number of cores, because by real observation, by real measurement, we can observe that C and M, these two components, are subject to different behavior with respect to the number of concurrent of the used core. So essentially, we have to rewrite this equation in this way, where we have a dependence between, from the number of concurrent threads, the number of used core. So by using this formula, and if we want to move from the task execution time to the throughput for a given p-state, we simply can calculate the throughput while dividing 1 divided the execution time. So the throughput for a given p-state can be expressed as a ratio between 1 divided Cn plus Mn. And in short, if we solve this set of equation, the system composed by this set of equation, we can calculate Cn as a function of a specific p-state, the frequency of a specific p-state, the throughput of the p-state of another p-state, and the throughput with the previous p-state. And similarly, we can calculate Mn. In short, we can calculate, we can estimate Cn and Mn by sampling only two curves while changing p-state. As you can see here, these points represent two random selected curves that we can sample. We can measure the power the throughput for all these in all these points. And in all these points, using the analytical model, we can predict all the curves while changing p-state. So we can use the analytical model for predicting the throughput for whichever p-state. Similarly, we can build an analytical model for estimating the power consumption. Based on various literature study, we can see that the power consumption, the power usage of a given task can be calculated as the sum of three components. The first one is the dynamic power usage, which is due to the switching operation between inside the transition, inside the CPU transistors, and can be approximated by this formula. The dynamic power is proportional to rho, which is the switching probability, the system capacitance, the voltage supply, the supply voltage, and the frequency. Obviously, frequency and voltage are directly correlated, because when I change the voltage, I change the frequency, and when they change the frequency, I change the voltage. There is a linear dependence between them. So I can I can represent this equation using a single coefficient, which represent all the previous values, times F3, because here we have frequency here, and voltage depend on directly on the frequency. Similarly, the second component is an equation like this one, the so-called CPU leakage power, which is equal to the voltage times the number of transistors used within the specific package. Key design is a constant that depends on the CPU, on the specific design of the CPU, and also a high leak is a technology-dependent parameters. We can approximate this equation with something like this: P leak is equal to beta times F. And finally, the third component is the power usage of the system, which is independent of the frequency variation, which is fixed. We can assume that this is fixed and is represented by through P fixed. In this way, power usage can be represented, can be estimated by an equation like this one. Using this equation, we know the frequency of the execution frequency of a given core. We have to estimate these two parameters for each number of used core. So we can estimate for each core, for each p state, using this formula and these parameters, the real power usage with the given p state, depending on a specific number of cores. We can achieve this measurement by solving the previous, by using the previous equation, and shortly after some algebra, we can achieve something results where we can calculate alpha depending on t and b depending on t. And using these two parameters, we can build the final equation, which is this one. The power usage for a given p state PL is equal to the alpha t, where t is number of the core in this case, times this value of the frequency to the power of 3 with the same p state, and beta t times the frequency to the for the p state PL. And then we can add p fixed. P fixed is always the same value. In this case, if we want to analyze the complexity, the complexity of the power model depends on the number of configurations that we should sample, we should measure in order to instantiate the model. And as in the case of the exploration-based strategy, also in this case, we need just 2 times Nmax configuration. That is, we can explore just 2 throughput curves and measure the power consumption. These measurements are enough for instantiating the model, this model that you can see here, for estimating the parameters that you can see here. And in short, also with the power model, we can achieve a linear complexity. In particular, this is the linear complexity for instantiating the model, that is for taking the measurements that we need to instantiate the model, to assign values to the model parameters. And this case is equal to a big of Nmax, just depend on the number of used cores. I go faster towards the final experimentation, final comparison, where we can compare different approaches based on different scalability profiles. In this experimental comparison, we collected different test cases from very common benchmarks. Group R represents the high scalable workload. Group B represent application with the limited scalability profiles, and Group C represent application in which the worst case, in which the workloads leads to something like the profile 4. That is, while increasing the number of using core, immediately there is a performance loss. This is just a picture that shows the ability of the analytical models, the power usage prediction model and the performance model prediction error that we measured along this set of well-known benchmarks. The worst case, we measured the power usage model prediction error less than 5% in this case, and also performance model prediction error less than 5% in this case. So we can consider the sufficiently reliable, enough reliable, this kind of models. Comparing the exploration-based strategy and the model-based strategy with the baseline, a baseline that use a very simple strategy, starting from highest p state, select the highest number of cores for which the power cap is not violated, and then increasing p state until the power cap is not violated. So is a search strategy very simple that moves along one direction and after along the other direction. The other one is the high climbing search to find the number of core which provided maximum throughput, and then try to increase the p state until the power cap is not violated. Considering two metrics, the power cap violation percentage and the speed up based on throughput, we can observe that with the most scalable application, high scalable application, essentially there is no real gain, because this can be expected, because with the real scalable application, all the previous strategy are very effective, because the throughput cures are very simple to be explored. In the other case, with the group B, with the less scalable application, in some cases we have real advantages, but most advantages are achieved with the group C. Group C includes the less scalable applications. The previous one was an experiment with a power cap equal to 50 watts. Also, the other one provides similar results if we set the power cap equal to 70 watts. And this represents the aggregated results, as you can see, while increasing while moving from scalable application to less scalable application. These different strategies provide the best result. In particular, the central one, which is the exploration-based strategy. Also, the model-based strategy in this case in some cases provide good result, but not equal to the exploration-based strategy. There is only a single case where the the model-based strategy wins. Let me show you. Is this one? This case, this is only benchmark for which we observed that the model-based strategy wins. Let me summarize the results. In short, by making overall assessment of all these results, we can see that the test cases of Group A includes the application with the high scalable application, confirm that overhead introduced by this strategy is very low. On the other hand, all the other results clearly demonstrate the advantages in terms of speed up, in terms of power cap violation, if we take into account the scalability profile of the applications. And while moving from scalable workloads to less scalable workloads, the advantages become higher. The exploration-based strategy, in short, consistently outperforms all the other strategies, except that in one cases, in particular, in these cases, we observed that model-based strategies outperforms all the other techniques, while the workload profile was not so regular, was quite irregular. That is, the unimodality assumption was generally did not hold. So as a final observation, as a final result, we can say that the general results of this study show that the the exploration-based strategy, generally with this kind of problems, works well only if we assume that if we take into account that the profiles of the application can be subject to variation. In particular, if we assume that the unimodality assumption is true, in the most of cases, the exploration-based strategy works well. However, when the unimodality assumption does not hold, we need to use some more complex strategy, like the strategy used by the model-based strategy. So model-based strategies are generally more costly, but in some cases we need to use a model-based strategy in order to cope with the more complex case, with the more complex application profiles. All that I discussed so far really is just the start. Because we can consider a number of additional parameters to be optimized, a number of additional features, for example, clock modulation, T-states, idle sleep state, G-state, differentiated core frequency. There may be a lot of parameters to be considered as a control parameter to be estimated. The conclusion is that I think that only way to move along this direction is to build self-optimizing applications. Essentially because keeping into account the application scalability profile can be done only inside the application. outside of the application is not possible to identify the profile, the scalability profile of the application, because the throughput of an application in some internal is a kind of internal measurement. Outside of the application is not possible to identify, to know which is the real performance provided by the application in a specific time. Okay, I probably used just a few minutes more than my times. Thank you for the attention. If you have a question, if you have...
Thank you, Pierangelo.
Yeah.
This was a very interesting talk. Thank you very much. Is there any question from the audience? Okay, I have one, mostly out of curiosity. Could you please go back to, there was a slide where you were showing different scalability profiles of the applications. Not this one. Yeah, okay.
Okay, this one.
Okay, this one or the other one, it's the same. Okay. Could you please elaborate a bit more on those different scalability profiles? In particular, I am wondering when these different profiles are shown by the applications and what could be the causes of these profiles?
Yeah, sure. These four scalability profiles represent four different situations that we can find while changing the number of used core within a typical concurrent application, a multi-threaded application. For example, a scientific application where we can decide the number of concurrent threads that we can use. The typical profile that we can see in most cases is this one, where we're increasing the number of used core, the throughput increases, because this is the so-called the case of, let's say, embarrassing parallel problems, where we can divide the input data set into small data sets, and we can use the different core to process at the same time in parallel different subset of different data subsets. However, in some cases, we can identify something like this. We can find something like this or something like this, and this is due essentially to this is the case of application where the thread, the executions of the different threads require synchronization. From the in order, for example, to access shared data, but this also due to the concurrent usage of shared resources. For example, we know that the bandwidth between the different core, otherwise something like the cache coherence protocol, can create something like this, some effect like this, where we saturate the interconnection, for example, between different core and the memory. Or due to the access due to a high number of operation for keeping the for the cache coherency, we can increasing the number of used core does not produce any additional throughput. The last two profiles, profile 3 and in particular profile 4, typically can be observed in application where there is both a high contention on resources and also an high contention on data. Thread, for example, have to be synchronized by means of, typically we can use locks. In other case, we can use, for example, transactions. In other case, we can use something like other kind of protocols that optimistic protocols that cause the rollback of a parts of the work of the executed work. So in this case, the contention, the hardware contention and data contention can be so high that increasing the number of used core, like in the profile 4, does not provide any additional
I see. But do you expect that there could be some applications that show more variable profiles due to some different synchronization protocol, like flat combining or weight-free synchronization or something like that, so that you have this throughput that goes down and up and down and up? And in that case, my understanding is that there would not be unimodal, right? So you will have to find some kind of adaptation to the exploration-based strategy, but I think that the model-based one could be more effective in that case. This is my understanding.
See, it is exactly because the model of the exploration-based strategy typically works when the curves are quite regular, like this one. In the case we have irregular profile, for example, more than one peak. For example, the throughput goes down, then go up, goes down, go up. Using the designing and exploration-based approach is possible. For example, using specific variation of the high climbing search, but various generally, if we try to use variation of the exploration strategies, we go to the direction of increasing the cost of exploration, so that there is a given point where it is not more convenient using the exploration-based strategy. But when the profile becomes very regular, model-based strategies provide the best solution. Provide the best performance in terms of exploration steps, in terms of time to find the best strategy.
Great, thank you very much. Any other question from the audience? Okay, I think we are running out of time, so yeah, maybe thank you again, Pierangelo. Maybe it's time to switch to the regular session, which is going to be chaired by Dr. Romolo Marotta. So, Romolo, if you're there, yes, please go ahead.
Okay, can you see me and hear me?
Yes, perfectly.
Okay, thank you, Alessandro, for the presentation. So, my name is Romolo Marotta, and I'm a researcher from the University of Tor Vergata in Rome, Italy. And I'll be chairing this session. So there will be two talks, and each speaker will have 30 minutes for their presentation, including questions and answers. So before we get started, I recall that presenters can upload their presentation and papers to the Slack workspace. So all the audience can deeply later read them and maybe have a later discussion on this, also on Slack. So sorry. Clearly, if there is any question about the talk, please wait until the presentation is over, and please kindly mute your microphone when you are not speaking. So the first speaker is Nupa Samit from Tata Consultancy Services. I hope that I spelled correctly your name. So Nupur will present a performance evaluation of GraphCore Intelligence Processing Unit M2000 accelerator for text detection application. So
yeah,
you can proceed.
Yeah, thanks, Romano. I'll just share my screen.
Yeah, go on. Okay,
yeah, just let me know if it's visible. Okay. All right. Yeah, thanks for the confirmation. So good evening, everyone, and welcome to my presentation on performance evaluation of GraphCore IPU M2000 accelerator for text detection application. This presentation is part of Pecs 22 workshop that is co-located with ICTE. Myself, Nupur Sumit, and my co-authors are Karan and Manoj, and we are from TCS Research. There exists a dire need for high throughput implementation of modern deep learning neural networks that are seamlessly getting used in applications across domains. But as the neural networks evolve, they are becoming more and more complex with large computational and memory requirements that adversely affect the inference time. Additionally, there are many hardware choices available for implementing the DNNs, including GPUs, FPGA, high-end CPUs, or emerging hardware such as IPU from GraphCore. Benchmarking the new hardware against commercially available hardware platforms is a usual practice and is also the main focus of this paper. We realize the nature and computation or memory requirement imposed by the target application, if pre-analyzed, can be an important factor in narrowing down the hardware platform that can be used to deploy the target application. Furthermore, we discuss various parameters such as batch size, compute precision, power, etc. that needs to be considered before choosing an hardware for deployment in a production environment. In this work, we have evaluated the capabilities of target hardwares through experiments, but an alternative approach can be through hardware performance models that can be used to predict the inference time or throughput for a certain application. However, there are many concerns associated with performance models around their accuracy, accessibility, and assumptions while defining those models, etc. The hardware platforms considered in this work includes the GraphCore IPU, V100 and A100 GPUs, and Alveo U280 FPGA DPU. These hardware have considerably different capabilities that are listed on this slide. The GraphCore IPU, for example, supports FP16 and FP32 compute precisions and has computational power of 1 petaflops and 250 teraflops respectively for both these precisions. And it has a 900 MB SRAM cache per IPU available as in-processor memory. And the IPU M2000 contains 4 such IPU units that connect to the host PC through a 100 gigabits per second network link. The GPUs support INT8, FP16, and FP32 compute. And the FPGA DPU is a systolic architecture that supports INT8 precision within the resources that are available on the Alveo 280 FPGA card. It can house 3 DPUs that have 14 batch engines and can process 14 parallel inferences. Let's look at the target application now. So Craft is a CNN-based network used to detect text in seen and scanned document images. It contains operations that belong to standard CNNs, including convolution, batch normalization, ReLU, activation, max pool, upsampling, and concatenation. So Craft has a computational load of 32.7 gigaflops and a memory requirement of 184 megabytes. And its inference time on CPU and FPGA ranges in seconds and in hundreds of milliseconds on V100 and A100 GPUs. So the inference time that we were getting on commercial hardware were not acceptable in deployment in a practical use case. So we used compression to speed up the inference time for Craft. And in the process, we defined 7 compressed models for it. So these models are compressed by 14 to 80 times and have different accuracy loss based on their architecture and compression factor. The discussions on the compression method and the architecture for compressed model is beyond the scope of this paper, and the Craft model and its compressed architectures, we are only treating them as different workloads to evaluate the performance of GraphCore hardware and compare it with respect to other commercially available hardwares. We analyzed the Craft model computation and memory requirement by estimating them at a layer level granularity. So we used a flop counter to estimate the giga floating point operations for every layer, and memory estimates are obtained by calculating the size of the output feature at every layer. Based on this information, we estimate the required giga floating point operations per second, memory and memory bandwidth to process every layer to achieve a target throughput. So the table that's presented here presents the data, which is the computation and memory bandwidth to achieve a throughput of say 500 frames per second in this case. So in this context, the bottleneck layer has a computational load of 8.7 teraflops per second, and the memory requirement for this layer, memory bandwidth requirement for this layer is 14.65 gigabytes per second, and that bottleneck layer is actually the layer 24. So the model analysis actually helps us come up with certain architectural options for the FPGAs and can be used for a one-on-one comparison with the supported capabilities of target hardware platforms. For instance, here we have estimated the required compute / memory capability for a layer-wise processing and fully pipelined processing architecture for FPGAs. So we realize the required capacity is much higher than the supported in case of fully pipeline design, indicating FPGA won't be able to support a throughput of 500 frames per second, the assumption of the throughput that we started off with. On the other hand, in case of GPUs, the register file and annual cache falls short to accommodate the required memory size. And if we talk about the IPU, then the IPU compute as well as the memory that it supports is able to meet the required compute and memory requirements for the target model, which is Craft in this case. The table at the bottom left represent Craft throughput speedup obtained on GraphCore 4 IPU configuration. So we observe 200 plus FPS is obtained for all compressed models. So these are actual implementation results. And another observation is that models with channels equal to or a multiple of 2 of the powers of 2 actually achieve a better throughput as compared to other models. So this we are able to see in model C8 and C18. So C8 has layers which are a multiple of 2, and it's just 60 times compressed. But C18 is a more compressed model, but yet the throughput for C18 is less than the throughput for C8. So this observation we actually observed only in case of GraphCore IPU, whereas similar things were not seen for other hardwares that were considered here. So the speed up with respect to the A100 DGX for FP16 is about 1.33 times for what was achieved on the IPU system. And we also compare a single IPU and 2 IPU configurations with a standalone GPU and FPGA. So the throughput for 2 IPU configuration is 1.14 times with respect to the 1 IPU configuration. So this indicated that the throughput scaling is not linear. That is, if we double the resources, then the throughput actually doesn't get doubled. So we actually couldn't get much time to investigate the reason behind it, but we think that the probable reason can be saturation of the memory bandwidth, owing to the nature of the test model, which requires output from the convolution network during upsampling. The throughput variation of all IPUs with respect to batch size indicate a sharp increase for small batch sizes that attain a peak, and levels off after a batch size of greater than 50. So among hardware other than IPUs, we observe that DPU have higher throughput as compared to GPUs for batch size up to 12 images. But for batch size up to 20 images, A100 and V100 have similar throughput, beyond which A100 actually offers a higher throughput as compared to V100 GPUs. So, however, the IPU implementation offers higher throughput gains as compared to all the other hardware. So, by this analysis, we can actually say that so in this case, actually, we have a clear answer that for any batch size, IPU configurations are actually doing the best. But if we just look at the commercial hardwares, then batch size plays an important role in choosing a particular hardware for a certain deployment scenario. Like I just talked about it, like for lower batch sizes, FPGAs were doing better, but then for higher batch sizes, GPUs were giving a higher throughput. So we analyze the performance profile of the C6 model. So C6 is one of the compressed version of the Craft. And this we did using the Pop Vision tool that is available for the GraphCore hardware as part of the Poplar SDK that is used to compile the model for GraphCore hardwares. The C6 model contains 76 layers in total, including convolution, maxpool, batchnorm, and ReLU. So, in addition to these layers, there are some mathematical operations such as concatenations and upsampling. So, the profiling information is actually available in terms of clock cycles. but it's available only for the layers and not for the mathematical operations. So when we looked at this profile, we realized that the bottleneck operation for this the target application, the target task of this test detection is actually the stream copy, which includes test image transfer time over the network. So in this case, actually, it was not the compute of the IPU that was limiting the throughput or the memory, but it was the network bandwidth, which is used by the host to transfer the test images to the IPU hardware. So this was our observation for this particular use case of craft, but then such information can actually give insights on if some of the compute layer is the bottleneck, and then one can actually work around those compute layers and try to siphon further output or further throughput from the IPU devices, or it's actually true for any other hardware as well. So the dynamic power consumption observations are presented on the left. The 4 IPU implementation consumes more power as compared to 2 and 1 IPU deployments. So the FP16 compute consumes less power as compared to FP32 designs. But the gap between the two actually reduces once the batch size goes beyond 128. So this indicates that lower precision offers power as well as throughput advantages over higher compute precision, especially for the low batch sizes. So that can also be a deciding factor while choosing a precision batch size or a hardware in deployment. And the CPU, A100 GPU and FPGA DPU consumes higher power as compared to the 1 and 2 IPU configuration for all batch sizes. So the throughput, we also measure the throughput efficiency, which we define as throughput per unit watt, and a higher value denotes better deployment option. So we present throughput efficiency with the variation with the number of IPUs on the right side here. So we observe that 4 IPU configuration has maximum throughput efficiency of 0.61 frames per second per watt. So this can be attributed to the IPU microarchitecture, where memory and compute units are actually close by, and thereby the power is saved while transferring data between the memory and compute. And IPU configurations have higher throughput efficiency as compared to GPUs and FPGAs for all batch sizes based on our experiments. So in conclusion, Graph4 IPU M2000 is a new hardware available within memory processing capabilities to accelerate machine learning workloads. We use a compressed version of text detection model to evaluate its performance. Upon comparison with state-of-the-art hardware platforms, we realize IPU can support much higher throughput, especially in FP16 implementations. Additionally, we analyzed the profile of the target application and observed the network transfer from interfacing host to Graph4 system is the bottleneck. So on comparison across systems, that is CPUs and A100 DGXs, we find that the Graph4 system delivers maximum throughput across all batch sizes. Additionally, it delivers maximum throughput efficiency, which makes a good case for Graph4 to be adopted in data centers and by cloud service providers as an ML accelerator. So this brings me to the end of my presentation, and thank you for your attention.
Oops. Okay, thank you, Burk. We have some time, so if there are any questions from the audience, please ask. There are not, I have some. The first one is, if I understood correctly, there is a, let's say, a bottleneck in memory transfers. So even though we, let's say, keep apart that problem, and I was wondering if the problem with scalability, when you go increase the number of IPUs, can be, let's say, alleviated by trying to achieving weak scalability rather than strong scalability. So the idea is the device capable of processing more than one image, for example, at a time. So is that kind of approach feasible with the memory available, at least in this kind of problem? I hope that the question is clear.
Actually, I could not get the question. Can you please be kind enough to repeat it?
Is it feasible with this device trying to increase the number of images that are processed per time? So trying to achieve scalability, that a higher scalability in terms of weak scalability. So increase the input side, let's say, or having a higher parallel speed up.
Right. So IPU actually, while we were, discussing with the GraphCode team and then going through the documentation, so we came across that IPU supports both model parallel as well as this model partitioning kind of thing. So when we are actually, scaling the number of IPUs, the model copies are actually created on those IPUs, and the images are going in parallel to them. But something that's also possible is dividing the model and data parallelism. So something that's also possible is like splitting the model across IPUs if a model is too big. So one of the findings actually that I did not include into the presentation was that we were not able to run the native graph model on the IPU. So it just won't compile for us. It was going out of memory. So in that case, actually that model was actually too big, around 81 MB. So that was the reason we think that it was not able to compile on the hardware. But yeah, as you're asking, that such things like data parallel and model parallel, those things are possible on the IPU.
Okay, thank you. It's all for me. Again, if there are any questions from the audience, please ask. So no, otherwise, we proceed with the next talk. Okay, thank you, Nukur, for your very interesting talk. So welcome to the next speaker, which is Maximilian Meissner. I hope that I spelled it well. Who is a PhD student from the University of Würzburg, interested in energy efficiency aspects in the context of cloud computing. Maximilian will be presenting experience and guidelines for sorting algorithm choices and their energy efficiency, which is a joint work with authors from the University of Würzburg and Hewlett Packard Enterprise. So, the virtual floor is yours. We can see your screen, but we can't hear you. You have to enable your microphone.
Now you can hear me?
Yeah, perfect.
Okay.
Thank you.
Okay, so I'll start my presentation. Thanks for the introduction. As you already said, my name is Max, and I just recently became a PhD student here at the University of Würzburg in Germany. And I'm still exploring different ideas because, of course, energy efficiency in data center and with respect to cloud computing is a very broad topic with many possibilities and challenges. And in this particular work, experience and guidelines for sorting algorithm choices and their energy efficiency, we want to present a case study where we show that fairly small changes in software can have a large impact on energy efficiency. And we want to focus on sorting algorithms because this is a well-known and well-studied class of algorithms, and there are already studies which research the energy efficiency of different sorting algorithms, and we want to complement these studies. And in my presentation, I will first provide you with a short motivation. Why did we actually choose to make this study, this case study, and where do we think this complements these earlier studies? In the second section, I want to show you our experiment setup so you know exactly what we did. And then, of course, I will show you our results or a few of our results before I come to the conclusions. So for the motivation, you are probably aware of the fact that more and more services are placed in the cloud recently. And this leads to the data centers increasing in number as well as in size. And there is a prediction that by the year of 2030, which is not that far away. And the global annual data center usage of energy will be 1 petawatt hour. And this is even in the best case scenario. So this creates a lot of problems, of course. For the operators of data centers, the electricity usage constitutes a major fraction of the overall operating costs. And of course, because most of this electricity is produced by means of fossil fuels, this is very bad for the environment and affects every one of us. But of course, energy efficiency in data centers has already been researched, and there are many possibilities to increase the efficiency of data centers. For instance, by intelligently placing and consolidating services such that the servers are running at their most energy efficient utilization level, and you can power down idle servers. On the other hand, there are effective mechanisms for autoscaling, where you want to provide services running on your server just with the right amount of resources that they need, and you don't over-provision resources. Of course, what we already heard in the first talk today, the hardware itself, on the hardware level, there are many mechanisms that can be utilized to make data centers more energy efficient, for example, through dynamic voltage frequency scaling, where we try to find the optimal level of operating frequency and voltage, for example, of a CPU in order to find a good trade-off between performance and energy efficiency. We also can have different C states where we can power down individual components of the hardware which are not required at the moment, so that you minimize idle power consumption. But the hardware is still controlled by the software, and it has already been shown by previous studies that, for example, different enterprise resource planning softwares that are functionally equivalent can be very different with respect to energy efficiency, even if the performance is approximately the same. So it has already been shown that the implementation of the software itself can have a very large impact on energy efficiency, which is often not considered, especially in the context of applications which run only in not battery-powered devices. This has already been shown by studies that most software developers do not take energy efficiency into account when they develop their software, which is partially attributable to a knowledge gap on how to actually achieve better energy efficiency and what impact different design decisions on the software level can actually have on the energy efficiency. An exception to this rule is maybe battery-powered devices. So, of course, for developers who focus their work on battery-powered devices such as smartphones, energy efficiency is much more crucial. So in this area, there already exist more tools and studies. For example, modeling approaches which show the developer which part of an application could consume a lot of power. But there's a gap with respect to applications running not on battery-powered devices. And we want to contribute by researching the energy efficiency of sorting algorithms, which has already been researched for smartphones with respectively small problem sizes and without considering non-random data. So overall, the problem that we want to address is that in applications running in data centers, there is no or almost no consideration for energy efficiency with respect to the implementation of the software. In earlier studies, which focus on the energy efficiency of sorting algorithms, the problem sizes used are often small. There is no variety in input data. And many of these studies only focus on one implementation of each algorithm and using only one single device. So our contribution here is that we compare the energy efficiency of different algorithms when the data is not random. And we also use two implementations on two devices so that we can see that not every energy efficiency that we evaluate for an algorithm is a property of the algorithm itself, but it can also be just an attribute of the hardware or the implementation. So that's our contribution. And what we did is for our study, we used 6 commonly known sorting algorithms. Each algorithm was implemented in 2 different implementation variants. We used 2 state-of-the-art servers for our experiments, and we used data which is already partially sorted. which is in contrast to earlier studies which only use random data. And the study is intended as a case study to demonstrate that very simple design choices can have a significant impact on the energy efficiency. And we want to complement these previous studies by the means which I just discussed. So which approach did we actually take? What was our experiment setup? For our experiments, we used 2 state-of-the-art servers from HPE. We used differently sized CPUs from different manufacturers with different operating frequencies and with different memory sizes. So we wanted to opt for state-of-the-art equipment of data centers, which is not built for special purpose and is different with respect to CPU and memory. We measured the total power consumption of the entire server, so not only individual components, but the entire server. We have our server where we execute our algorithm that we want to evaluate. We have a dedicated control device which executes, which initiates the measurements and collects the data from the measurements and also the data from the power analyzer. For the sorting algorithms, we used 6 commonly known sorting algorithms with different time complexities, different space complexities, and each algorithm was implemented in 2 different variants. We did not consider hybrid sorting algorithms such as timsort, which are combinations of these. And we did not include, consider stability, the attribute of stability in sorting algorithms. In the following results that I show, I want to focus on merge sort, heap sort, and quick sort. First of all, insertion sort, bubble sort, and selection sort have quadratic average time complexities and are probably not often used in practice anyway for this reason. And the most interesting results are among these algorithms because they have very similar time complexities, with the exception of quicksort's worst case time complexity, and they have different space complexities, and we will see that this has a huge effect. So the implementation variants we chose for merge sort, implementation variant 1 uses pre-allocated memory. Implementation variant 2 uses dynamic memory allocation. For heap sort, variant 1 we use memory-based swapping of elements during the sorting process. For variant 2, pointer-based swapping. And the same for quicksort, variant 1 uses memory-based swapping and variant 2 uses pointer-based swapping. So these are very simple design decisions which we show will have a significant impact. Input data generation as a data type, we used integers. We used 3 different problem sizes, small, medium, and large. We chose the problem sizes such that they fit into main memory, such that the experiments run long enough, such that our power analyzer provides us with enough data that we can make statistical conclusions based on the data. And the input data was equally distributed across the respective servers' threads. And an important distinction to earlier studies on this topic is that we not only use random data, as has done by, for example, by this previous study, we also use data that is pre-sorted to the extent of 20%, and another data set which is pre-sorted to the extent of 50%. How did we calculate the efficiency? So our power analyzer samples the power measurements with a frequency of 10 kilohertz and aggregates these over 1 second. So for each second, we get a report of the power consumption of the entire server. If we sum this up, we get the energy. And we then calculate the energy efficiency or the efficiency of the algorithm execution, basically by dividing the amount of data through the energy that we measured during the time it took the algorithm to work through this data, basically. And the unit is then byte per watt second or byte per joule. We ran each configuration 5 times. So each configuration is a combination of server, algorithm implementation, problem size, and data sets. And then over these 5 runs, we calculate the mean energy efficiency. And in the paper, we also calculate the 95% confidence intervals. and look at if the confidence intervals of the different implementation variants of an algorithm do not overlap, then we determine that there is a statistically significant difference between these implementations. Now, in the following, I will show you some of the results in our paper. For each algorithm, I have basically 4 graphs, each for a combination of server and implementation variant. And then within each graph, the axis is the efficiency that we calculated in kilobyte per watt second. We have here the 3 groups which constitute our 3 data sets. Here the random data set, the data set which is already to 20% pre-sorted, and the data set which is to 50% pre-sorted. And within each data set, we have the different problem sizes, small, medium, and large. And on this example for heap sort, for instance, we see that heap sort on server A has a fairly stable efficiency of around 150,000 kilobyte per watt second. So we don't see a lot of change here with respect to implementation variant or the data set or the size of the data set. However, on server B, we see that this is quite different. Here, when the data is already pre-sorted to 20%, and then the algorithm is more efficient than when it is, for example, completely random data. And here again, we don't see a significant difference between the 2 implementation variants. So we determined that for heap sort, the 2 implementation variants that we chose do not exhibit a statistically significant difference with respect to efficiency. But we also see that the server has an influence of the efficiency of the algorithm, of course, which needs to be kept in mind when we try to interpret such results, which also needs to be taken into account when we look at earlier studies which only executed their experiments on 1 device. So when we move to merge sort, we see, first of all, merge sort is much more efficient than heap sort. So heap sort was in the area of 150,000 kilobyte per watt second. Here with merge sort, we are already in the worst case. Here it's 3 million, which is of course much, much more. And we already also see that the implementation variant has a significant influence on the efficiency of merge sort, because of course we have here different scales. If we adjust the scales, the picture looks like this. So merge sort with pre-allocated memory is significantly more energy efficient than merge sort with dynamic memory allocation. And this is a property of the implementation. We see that this happens on both servers. When we move to quicksort, first of all, what we see is that quicksort is more energy efficient than heap sort in some circumstances, but much less energy efficient than merge sort. We see that implementation variant 1 has the energy efficiency of implementation variant 1 significantly decreases when the data is already pre-sorted to some extent. So quicksort has a worst case execution time which is quadratic with respect to the input. But for the 2, and this often depends on the selection of the pivot element in quicksort. But for both variants, we actually chose the pivot element in the same way. So this seems to be a property of the implementation with respect to how we chose, how we execute the swapping. So we can see that implementation variant 1 is more energy efficient on random data, but implementation variant 2 is much more energy efficient on non-random data. When we calculate a few differences, so these are the comparisons of the best results of each algorithm with respect to change in %. When we compare merge sort and heap sort, we see that merge sort is more than almost 2,000, approximately 2,000% more efficient, as there's a change in efficiency of about 2,000% on random data on server A. When the data is pre-sorted, we even have a much larger difference in efficiency from 4,700% to 5,400%. And when the data is 50% pre-sorted, also in the same area, 4,000% to 5,000% approximately. In server B, the numbers are sometimes higher, sometimes lower, but we can determine that merge sort is significantly more energy efficient than heap sort. Quick sort, again, is more efficient than heap sort, but less efficient than merge sort. So on server A, for instance, the difference is 329% to 394% on the random data, 232% to 391% on the pre-sorted data. And yeah. So in summary, we can say that merge sort variant 1 outperforms all other algorithms by a large margin with respect to efficiency. On server A, the variant 1 is 6 to 14 times more efficient than merge sort variant 2. And on server B, variant 1 is 2 to 10 times more efficient than merge sort variant 2. So dynamic memory allocation reduces the energy efficiency significantly in our experiments. Heap sort has been the least efficient algorithms of these three. And the difference between the implementation variants is mostly not significant with respect to heap sort. In quicksort is most of the time more efficient than heap sort, especially on random data. But we have seen that the energy efficiency of variant 1 decreases significantly when the data is already pre-sorted. So our guidelines based on our experiments, what we would say is that merge sort is preferable over all other investigated algorithms in the case that memory is no constraint. And if you implement merge sort, pre-allocation of memory is preferable. And if this is not possible, then quicksort can actually be a better alternative. Quicksort is preferable over heap sort if memory is not a hard constraint. When the data is already pre-sorted, then pointer-based swapping of the elements during the sorting process has been much more efficient in our experiments. When the data is not pre-sorted, memory-based swapping is slightly more efficient. Heap sort in our evaluation is only preferable when memory is a hard constraint. So to conclude, in our study, we compared 6 commonly known sorting algorithms on 2 state-of-the-art servers with 2 implementation variants, 3 problem sizes, and the major difference between our study and earlier studies that we used also pre-sorted inputs, which have shown to have a significant impact on the efficiency of the algorithms. And we can see that there are major differences in energy efficiency even between algorithms with an average time complexity of n log n. And we have seen that the characteristics of the input data needs to be taken into account. So earlier studies, the results of earlier studies which only used random data or only used one device, these results should be handled with care because, of course, the hardware itself has also a significant impact. It's very difficult to really fairly evaluate the efficiency of an algorithm without considering the hardware which it is running on. We have also seen that small changes in implementation can have a significant impact on energy efficiency. And this was basically one of the major reasons for why we conducted this case study, because most software developers are not aware of the fact that small changes can have a significant impact on energy efficiency. And that's what we wanted to show. Future work should further investigate the causes for the difference in energy efficiency. In our experiments, we did not record low-level hardware information, so we can only speculate for why on different hardware the efficiencies fluctuate so strongly. And it would be possible in addition to our guidelines, if you can evaluate the causes for the efficiency or inefficiency of an algorithm in certain situations, then you could also in future work implement an adaptive system where you basically choose at runtime the best algorithm for the situation that you currently have. But this is only future work. And with this, I want to conclude my presentation and thank you for your attention.
Okay, thank you, Maximilian. So we will go ahead and we have some time for questions. So if the audience has some, please ask. Okay, I have some. Okay, I will start with have just a curiosity. If you have some idea, say for the, let's say, strange behavior of platform B, I think, in your experiment, when for different percentage of random partially sorted data, because there is a kind of bell shape, let's say, from 0% of already sorted data, let's say, not controlled, so that variable, and 20%, and then 50%. So there is an increase in efficiency and then a decrease. And that is quite, I don't know, for me it's quite surprising, let's say, to see, because that pattern isn't present in the platform A, if understood correctly. So I was just curious if there is, if maybe you have some idea about that.
Are you referring to a specific graphic here?
There is quite common in, I think, in all graphs, because there is present here in with match sort, but I think that it was already present with also heap sort, I think. Yeah, exactly. I don't recall with quick sort, but I think that it's very similar shape, let's say. Okay. So I was curious if you have some idea about that kind of behavior. Maybe there is some architectural difference between the two servers. I don't know.
Yeah, if we don't observe this pattern, for example, on server A, so I assume it is a property of the hardware itself, because of course all other things are equal here. So the difference between the servers is the CPU manufacturer, the frequency, and the memory size. But I'm not sure how this actually affects is affected by the degree to which the data is already pre-sorted, because I would assume that the degree to which the data is pre-sorted affects the algorithm itself, not the hardware. So I actually, at this point, do not have a very satisfying answer to how this behavior comes into reality on server B. And of course, we only have 3 different data sets. So to really see what this distribution would look like, we would need to make much more measurements with equal steps, for example, from random to completely pre-sorted in 10% steps or something like that.
Just to have another point of view, what about caches? Just of course, the amount of cache per core, let's say per thread, from the two different data, if you know that data, just a curiosity, because maybe that would be have an impact. I think that kind of data doesn't show, right?
I didn't really understand you.
What about caches? What about cache per core? In how much different is the cache from the two different architectures? If you know, if you recall that, just a curiosity.
No, sorry, I don't can recall this from the top of my head. But of course, this kind of hardware difference would be important to explore. Maybe there might be a possible explanation for the difference in behavior.
Hey, Max.
Okay.
Hi. Yeah, hi, Klaus. Yeah. Do you know the difference?
Yeah, that's 2 major different architectures we use there, and the cache is significant differently, the levels and the sizes of it, and that can, I'm pretty sure, has some kind of an impact in this, but we have not further investigated that at this point. But it says 2 major different CPU vendors, and they have a significant implementation of the cache, the multi-level caches there.
Yeah, thanks, Claude. For everyone listening, Klaus is one of our co-authors.
Okay, thank you for this answer. Actually, I have another question. I was wondering if you could be interested in, also in your future work, in studying, let's say, more deeply the, let's say, asymptotic inefficient algorithms, because actually that kind of algorithms are quite known to be effective for small-scale problems, so that they can exploit very well caches again. So I was wondering if it might be interesting studying, for example, repeated processing of, so repeated sorting of different workloads with different data, clearly, with, that are characterized by a small data set. So the idea is, okay, it's not memory the problem, but maybe in that case, the, let's say, step efficiency could be interesting somehow, no? Because your metric of efficiency is somehow related with the amount of data, okay, quite resembling asymptotic cost, asymptotic analysis. And so I was wondering if it could be interesting analyzing the step efficiency, because constants sometimes matter, especially when we're working with small data sets that can really benefit from caches. Is clear the question?
Not entirely. So you asked about step efficiency, if this is something that we want to study in the future.
Okay, that's the question. Is you were interested in studying the single step efficiency, let's say, because that constant could be relevant in choosing the algorithm, even inefficient algorithms, in case of small scale inputs.
So we actually did not discuss yet what we want to do in future work. So of course there are many possibilities how to extend this, but of course this is one possible and interesting topic that we could explore.
Okay, thank you for answering me. So I think that's all. So thank you again, Maximilian, for your very interesting presentation. Okay, so great. Thank you, everyone. I appreciate it being here. So the session is finished. And thanks to all for joining us today. Hope to see you soon, next time. So I give the word to our General Chair, Alessandro Pellegrini, for the closing session.
So yes, we are a bit ahead of time on the schedule, which is much better than being late. So, well, this is the end of Pecs 2022. I really want to thank again all the authors and ICP workshop organizers. And of course, also, I would like to thank all the participants. I personally think that this has been an interesting workshop. I hope you enjoyed the talks as much as I did. We, of course, look forward to seeing you at Pecs 2023, which hopefully will be in presence eventually so that we can meet face to face. So to conclude, I wish you a very nice weekend, and I wish you to enjoy a very successful ICP 2022 conference. So thank you again for joining, and see you next time. Bye to everybody.
Bye.
Bye.
Bye, thanks again.